Okay. Then next we will take an example of like that, right. So, just we will see that how things are happening. Suppose you have a 3 bus problem, 2 generators, right. Here it is power because Pg1 and here power Pg2, right. So, voltage here it is given V1, that is 1 angle 0, right, and this is bus 1, this is bus 2, V2 it is 1 angle delta 2, right, and V3 is equal to 1 angle delta 3, this is bus 3, and PL3 is given 2 per unit, because here everything we are dealing with real power only. So, no Q is required, and line 1 to 2 is actually not connected, right. So, this and V3 also 1 angle delta 3, right. So, Y bus matrix is given actually for this network, Y bus matrix is given, right. So, it is 1 minus J 10, second one is 0, Y 1 2, because 1 to 2 actually not connected, right, and this is minus 1 plus J 10. So, from this thing you can make out that line charging admittance not considered, because if you sum up all the elements of this row, it will become 0, because 1 minus 1 will be 0, minus J 10 plus J 10 will be 0. So, for any row if you sum up all the elements, whatever will be left, that is actually your charging admittance, but in this case charging admittance is not considered. Similarly, this is 0, this is 0.5 minus J 5, this is minus 0.5 plus J 5, right, and this is again this one and this one same, Y 1 3 Y 3 1. So, minus 1 plus J 10 minus 0.5 plus J 5, and this is 1.5 your minus J 15, right. So, this Y bus matrix is given, and for these two units that incremental cost characteristic is given, that is IC1 is equal to 4 plus 0.6 Pg1, and here it is IC2 is equal to 4 plus 0.6 Pg2. This is given, these are given. You have to find out the optimal generation scheduling. So, what will be the optimal generation scheduling? That is why you have to find out Pg1 and Pg2, right. So, that means, and at bus 3 no generator is there is a load at 2 your this thing. So, just I will show you the step how one can manage it, right. So, we know Pi is equal to the power injection from the load flow studies, the general formulas we know that Pi is equal to K is equal to 1 to n, that magnitude Vi, magnitude Vk, magnitude Yik, cosine theta ik minus delta I plus delta k, right. Therefore, Pi is equal to, we can write this equation, we can write like this, that K is equal to 1 to n, then magnitude Vi, magnitude Vk, magnitude Yik, cosine in bracket theta ik minus delta I minus delta k. This one we are taking minus common, and in bracket we are writing minus delta I minus delta k, right. That means, Pi is equal to K is equal to 1 to n, then magnitude Vi, magnitude Vk, magnitude Yik, and in bracket we are writing cosine theta ik. I mean this equation, that cos A minus B, cos A cos B plus sin A sin B. So, we are writing cos theta ik cos delta I minus delta k plus sin theta ik sin delta I minus delta k, right. Now, we assume that delta I minus delta k, let us write, is equal to delta Ik. That means, delta Ik is equal to delta I minus delta k. This you assume, right. Then this equation can be written like this, that Pi is equal to K is equal to 1 to n is Vi Vk Gik, your what you call, if you put here that your it is cosine, it will be cosine delta Ik, and this will be sin delta Ik then, right. Therefore, Yik magnitude, when you multiply by magnitude Yik, so it will be your magnitude Yik cos I theta ik will be your Bik, right, and your Yik your sorry Gik, and this is your what you call that and Yik sin theta ik will be your Bik, right. That means, this equation, that when you do so, it will be then K is equal to 1 to n Vi Vk, it will be Gik cosine delta Ik plus Bik sin delta Ik, right. That means, your Yik cosine theta Ik is Gik, and Bik your is equal to that Yik your sin theta Ik, Yik magnitude, right. So, where I have written here, where Yik cosine theta Ik is Gik and Yik sin theta Ik is equal to Bik, and Yik is equal to Gik plus J Bik, right. Now, for the sample power system, as it is given magnitude V1, magnitude V3, magnitude V3, your all are 1 per unit. That means, in this diagram, your magnitude, what is 1 angle 0? So, magnitude is 1. Similarly, it is 1 angle 0. Magnitude bus 2 also voltage magnitude is 1. bus 3 also 1 angle delta 3. So, voltage magnitude is also 1. So, all the buses we have assumed voltage magnitude actually it is 1 and it is a 3 bus problem. So, it is n is equal to 3, right. Therefore, put k is equal to 3, that is because n is equal to 3, right. Therefore, Pi is equal to k is equal to 1 to 3, then it is g I k cosine delta I k plus b I k sin delta I k, right. Now, for I is equal to 1, you expand this equation. For I is equal to 1, you will get P 1. So, it will be g 1 1 plus g 1 2 cosine delta 1 2 plus b 1 2 sin delta 1 2 plus g 1 3 cosine delta 1 3 plus b 1 3 sin delta 1 3. This is say equation 2, because this one actually we have marked this one as equation 1 here, right. So, similarly for I is equal to 2, put I is equal to 2 and expand, right. So, P 2 will be equal to g 2 1 cosine delta 2 1 plus your b 2 1 sin delta 2 1 plus g 2 2 plus g 2 3 cosine delta 2 3 plus b 2 3 sin delta 2 3. This is equation 3, right. So, next is your put I is equal to your what you call I is equal to 3, you will get your g 3 1 cosine delta 3 1 plus b 3 1 sin delta 3 1 plus g 3 2 cosine delta 3 2 plus b 3 2 sin delta 3 2 plus g 3 3, right. So, if you expand this this thing, so naturally one case will happen that everywhere you will find there are 5 terms, but according to here 2 terms are there, well, then there is no 6 term, 5 terms, because for anywhere you will find that your this when sin delta 1 minus delta 1. So, it will become 0, sin 2 sin delta 2 minus delta 2 will be 0. So, that is why everywhere when you expand it is 5 terms, right. Now, this something this one that delta 1 2 and delta 2, just hold on, that delta 1 2 and delta 2 1 is equal to 0, because line 1 2 actually not connected, right. And then we can write delta 3 2 is equal to minus delta 2 3 and delta 1 3 is equal to minus delta 3 1, because delta 3 2 is equal to delta 3 minus delta 2. So, that one we can write minus in bracket delta 2 minus delta 3. So, that is minus delta 2 3. Similarly, here also delta 1 3 is equal to minus delta 3 1, because delta 1 3 is equal to delta 1 minus delta 3. So, minus if you take common delta 3 minus delta 1 is equal to minus delta 3 1, right. So, this equation, that equation for P 1 P 2 P 3, equation for P 1 P 2 P 3, all these things delta you substitute, delta 1 2 is equal to delta 2 1 0 and other thing you substitute. If you do so, you will get P 1 is equal to g 1 1 plus g 1 3 cosine delta 3 1 minus b 1 3 sin delta 3 1, right. Similarly, P 2 is equal to g 2 2 plus g 2 3 cosine delta 2 3 plus b 2 3 sin delta 2 3, and P 3 is equal to g 3 3 plus g 3 1 cosine delta 3 1 plus b 3 1 sin delta 3 1 plus g 3 2 cosine delta 2 3 minus b 3 2 sin delta 2 3. This is equation 7. Now, from the y bus matrix we have this all this y bus, you have this thing, you have the data, right, you have the data. This is actually this is your g 1 1 1, right, your what and b your 1 1 is minus 10, right, but all the this sorry, it is g 1 1 is 1, then g 2 2 is your 0.5 and g 3 3 1.5, right. Similarly, if you say that your what you call that b 1 3 b 3 1 all are given, b 2 3 b 3 2 all are required. So, whatever there g and b from this equation you will get it, right, from this equation you will get it, y is equal to g plus j b, right, from here you will get it. So, use all the parameters are there, then you substitute all this g and b parameters, you substitute, right. If you do so, just hold on, if you do so, then P 1 will be 1 minus cosine delta 3 minus 10 sin delta 3 1, this is I have marked equation 8, right. P 2 will be 0.5 minus 0.5 cosine delta 2 3 plus 5 sin delta 2 3, this is equation 9. Similarly, P 3 is equal to 1.5 minus cosine delta 3 1 plus 10 sin delta 3 1 minus 0.5 cosine delta 2 3 minus 5 sin delta 2 3. This is equation 10, right. Now, power loss expression can be obtained as we know the sum of injected power is the power loss, that means P loss is equal to sigma I is equal to 1 to 3 P I, that is equal to P 1 plus P 2 plus P 3, right, is equal to that P 1 plus P 2 plus 3 you sum it up, right, this 3 you sum it up, you will get 3 minus 2 cos delta 3 1 minus cos delta 2 3, right, this you will get. That means, this one, this equation also can be written like this 3 minus 2 cos, this one written as delta 3 minus delta 1 minus cos delta 2 minus delta 3, this way this is the equation, this is the last one, right. Next is that you take derivative of this thing your this delta P 2 and delta P 3, take all the derivative, right. Then what will get that if you take the derivative that delta P 2 delta P dP 2 d delta 2, take the derivative dP 2 d delta 2. So, this is actually P 2 is written, it is written cosine delta 2 minus delta 3, it is written 5 sin delta 2 minus delta 3, right. So, actually this equation, this P 2 equation actually like this, right. Similarly, for P 3, P 2 actually it is 0.5, right, minus 0.5, then cosine it is delta 2 3, right, delta 2 minus delta 3 plus 5, this sine, this is also delta 2 minus delta 3, this way, right, this way you write and take the derivative. Therefore, your dP 2 upon d delta 2 you will get 0.5 sin delta 2 3 plus 5 cos delta 2 3. Similarly, dP 2 by d delta 3 you will get minus 0.5 sin delta 2 3 minus 5 cos your delta 2 3. Similar way for P 3 expression you write cosine delta 3 minus delta 1 plus 10 sin delta 3 minus delta 1 and so on, this way you write, right. Sorry, this one we take dP 2 by delta 3. Similar way you find out dP 2, similar way dP 3 upon d delta 2 and dP 3 upon d delta 3 you take the derivative, right. Similar way make it and take the delta 3 1 you write cosine delta 3 minus delta 1 here plus 10 sin delta 3 minus delta 1 and so on. This way you make it and get all the dP 2 d delta 2, dP 2 d delta 3, dP 3 d delta 2 and dP 3 d delta 3. So, this is the expression you got, right. And also dP 1 d delta 2 is 0 because P 1, right, your what you call dP 1 that P 1 is not function of delta 2, nowhere delta 2 is appearing in equation 8, no delta 2, that is why dP 1 delta 2 is equal to 0, right. And dP 1 your d delta 3, dP 1 d delta 3, that is here function of delta 3, you can take the derivative dP 1 d delta 3. So, that is coming sin delta 3 1 minus 10 cosine delta 3 1. So, take this derivative, right. Only thing is that you will make it all your delta 3 minus delta 1, here also sin delta 3 minus delta 1, this way you take the derivative. Once you do so, then this that equation 76 whatever we have derived, it will be reduced in this form. So, this matrix will be dP 2 d delta 2, dP 3 d delta 2, dP 2 d delta 3, dP 3 d delta 3, and it will be your only one bus 1 is slack bus, right, and one bus is a load bus and one bus another bus is a generator bus. So, that is bus 2. So, is equal to 1 minus dP loss dPg 2 and this will be 1 is equal to minus this is 0 and this will be dP 1 d delta 3, right. So, your because dP 1 d delta 2 is equal to 0, dP 1 d delta 2 is equal to 0, but dP 1 d delta 3 exists, that is why we are instead of writing dP 1 your d delta 2 again, here actually dP 1 d delta 2 is equal to this 0 we are putting here, this is equation 12, right. Now, next is you have to calculate delta 2 3 and delta 3 1 corresponding to a particular Pg 2. Delta 2 3 means delta 2 minus delta 3 and this is delta 3 minus delta 1 corresponding to a particular value of Pg 2, right. So, you assume because bus 1 is a slack bus, bus 2 is a generator bus and bus 3 is a load bus only. So, you assume initially say Pg 2 is equal to Pg 2 0 is equal to 1 per unit, let us assume this, right. Therefore, P2 power injection at bus 2 is equal to actually Pg2 minus PL2, there is no load at bus 2. So, it is actually P2 is equal to Pg20 is equal to 1 per unit, right. That means, from equation 9 actually, that is your P2 expression, just let me find out, right. That means your this one, right. So, from equation 9, that means this equation, your this equation, right, that is P2 is equal to Pg20, this equation. So, that means we are writing this one, that 5 sin delta 2 3 minus 0.5 cosine delta 2 3 is equal to 0.5. This is a nonlinear equation, right. So, this is solving above equation iteratively, we get delta 2 3 11.5 degree. Actually, I have made some trial and error, right. And so, some from your intuition, some value you choose such that this equation satisfy left hand side and right hand side satisfy. So, delta 2 3 actually 11.5 degree approximately I have got, right. Now, at bus 3 only load is there, but generation is not there. So, power injection is minus 2.0, right. So, you go to equation 10, there you can write it, that is equation let me see where equation 10, right. This is equation 10, right. So, this is actually equation 10, right, and your delta 2 3 you have got 11.5 degree, delta 2 3 you have got 11.5 degree. So, in this equation 10, this cosine delta 2 3 sin delta 2 3 all you get and simplify this equation, then you will get, and P 3 is equal to your minus 0.20 at the bus 3, right. Then you will get 10 sin delta 3 1 minus cosine delta 3 1 is equal to minus 2.0132. So, again by trial and error only I have got delta 3 1 approximately minus 5.85 degree, right. So, this delta 2 3 and delta 3 1 I have got it, right. So, at and your this thing at slack bus, that P 1 is equal to Pg 1, right, that is at bus 1. You can see the diagram I have shown you, P 1 is equal to Pg 1, that means this one your just see where the diagram has gone, just hold on here, right. So, here. So, here. So, here it is your P 1 is equal to Pg 1, right. So, from equation 8, that we as P 1 is equal to Pg 1. So, actually P 1 is equal to this expression was given. So, that is actually writing Pg 1, right, is equal to 1 minus cosine delta 3 1 minus 10 sin delta 3 1. So, Pg 1 after putting delta 3 1 values, right, we are getting actually 1.024 per unit, right, and it is given the cost characteristic, it is given that your IC 1 is equal to, that incremental cost is given, that IC 1 is equal to 4 plus 0.6 Pg 1 is equal to 4 plus 0.6 into 1.024, that is 4.6144, right. Similarly, IC 2 is equal to 4 plus 0.6 Pg 2 is equal to 4 plus 0.6 into 1, that is 4.60, right. This we are getting. Next is that your solving equation 12, right, that means this equation, that you are just hold on, right, just hold on, this equation, right. So, then all these as all the delta values we have got. So, in this expression, that is equation 12 dp 1 d delta 3 compute, all these things are there, delta values you have got it, you put it, right. So, if you do so, if you compute, I am giving the final answer only, right, final answer only. So, in that case you will get that L 2 is equal to that your first you will get 1 minus dp loss upon dpg2, and L 2 that is your penalty term, right, L 2 is equal to 1 upon 1 minus dp loss upon dp, that is 1.0203, this you will get, right. But for L 1 it will be 1, right, we have seen this before. Therefore, but L 1 IC 1 is equal to 4.6144, right. So, this one actually this is your IC 1, this is your IC 1 computed. So, L 1 is 1. So, L 1 that is 1 into 4.6144. So, that is this one, right, and L 2 you got 1.0203, that means, but this is your IC 2 4.60 multiply by 1.0203, you will get 4.6933, but for optimal solution both should be equal, but here it is not equal. but because L 2 I C 2 much greater than your L 1 I C 1, therefore, we need to decrease P G 2, right, because it is more than that. So, that means this is an iterative process. In the classroom purpose, we cannot do that iteration, right, but after few iteration result will become actually delta 2 3 11 degree, delta 3 1 will be minus 6 degree, and P G 1 will be 1.05 per unit, right, and that is the slack bus power whatever it will be there, and P G 2 actually 0.963 per unit, and L 2 will become 1.01792, and at that time L 1 I C 1 approximately equal to L 2 I C 2 will become 4.68. This is the step, right. Let me tell you, this is actually to show you how things work, right, but it is not like that, that in the classroom we will do so many iterations and this that. This is only steps are shown that how one can solve this. So, you may have to do few calculations only, right, but as far as classroom is concerned and your this iterative process or in the exam hall also we cannot give like this. Similarly, your what you call, this is just to show you the your what you call few step, right. So, this is actually optimal economic load dispatch whatever I mean possible learning in the classroom, only that much we have talked, right. So, once so next so we have assumed that transmission loss formula. So, now we will try to derive that your transmission loss formula, right. So, next come to the transmission loss formula. So, consider now this is actually a transmission loss formula, right. So, we have to derive this, just hold on, just 1 minute. So, now this suppose you assume this is actually your what you call schematic diagram showing two generating units. This is generator, look at this side only, this is your generator 1 and this is your generator 2, right, and it is connected to transmission lines. There are so many bus bars. So, schematically we are representing load current, total load current say I L, right, and one particular branch it is say kth branch, right. So, your current through that branch is your I k, right. This is that means we are just first we are assuming only two generators, after that we will generalize that, right, and we but to get this transmission loss formula we have to make few assumptions that will come later. Now, that means it is a transmission network, it has a number of buses, right. Load current, total load current is I L, right, and one particular branch K having current I k, and two generators basically your what we call current from generator 1 generator 2 is I G 1 and I G 2, right. Now, you assume that the total load current are supplied by the generating station 1. So, we assume the total load current supplied by this one, right. That means, generator 2 is off. So, at that time that current through branch your K say it is I k 1, right, because generator 1 is supplying the current. So, kth branch current will change, right, but total current I L supplying by the generator only, right. So, this is generating station 2 is off. So, it is off, right, it is open, right. So, in that case what will happen? So, and the current through this is I k 1. So, in that case what will happen, that let the current in the line cab written be I k 1, right, and let us now define A k 1 is equal to I k 1 upon I L, right. You just define a term I k 1 upon I L, right. Later we will see that A k 1 actually it is a real quantity and I will apply a simple superposition, right. So, this is equation 78, right. So, similarly, in figure B here you assume that generator 2 is supplying all the load currents, but generator 1 is off, right. That means, current through this branch K is I k 2 and right, and because here also your branch current this one will change, right. So, generating station 1 is off, this is figure B. So, in that case you define another term A k 2 is equal to I k 2 upon I L, right. This is another term, this is equation 79. So, this A k 1 and A k 2 these two terms are defined, because we have to make some approximation, right. So, A k 1 and A k 2 generally we make it as a current distribution factors, right. So, once your what you call this making such kind of arrangement for analysis, right. Now, when both the generators are supplying current into the power network as shown in figure 10, right. That means, here it is figure 10, right. So, this thing your what you call that this both the generator when supplying power Ig1 and Ig2 together, right. So, at that time current through branch Ik, this one actually you apply superposition. So, in that case what will happen that Ik you can write AK1 into Ig1 plus AK2 into Ig2. So, this is actually 80, this AK1 AK2 are the current distribution factor, right. Now, we will make certain assumptions. So, assumptions are that for all network branches ratio x by r is same. This is actually very bad assumptions. For transmission line x by r ratio is not same, it varies actually, because we use different type of conductors, right. But we will assume that x by r ratio is same, right. Second thing is all the load currents have the same phase angle. This is also not true, but we will assume that for approximation, right. So, this based on these two assumptions we will make your what you call that we will derive that loss formula, right. So, to for this assumption we will do something, that why we are making this assumption. Suppose consider bus I, look at this one, right, of the network as shown in this is figure 12. This is bus I, is voltage magnitude V I angle delta I, and current through this load actually is ILI, right. So, a load is equal to PLI plus JQLI. So, we know from figure 2 we can write no, in general P minus JQ is equal to V conjugate I. That I is equal to P minus JQ upon V conjugate, we know that. So, that means this load current ILI we can write that is your PLI minus JQLI divided by VI conjugate, right. That means, if this one next ILI can be written as the root over PLI square plus QLI square and angle is minus phi I, right. Phi I is equal to your what you call this actually tan your this thing tan inverse QLI upon PLI, right. So, this angle load angle you can write like this minus phi I, right, and this one voltage magnitude V I, it is conjugate, its angle is delta I, that is conjugate. So, it is minus delta I, right. Therefore, ILI is equal to root over PLI square plus QLI square upon magnitude V I, and this is minus delta I. So, it will go to the here it is positive. So, it is angle delta I minus phi I. Now, this is the your what you call your load angle, load current angle at bus I, but what we will do this delta I minus phi I we will assume they are same for all the load current. That means, since delta I and phi I vary only through a small range, in reality may not be not, but we will assume that, right. It is quite practical to assume that delta I minus phi I is equal to say beta I is same or right for all load currents. That means, for all the load currents we will assume this is same, right, for the all load currents. If it is so, then your what you call, right, that phase angle of IK1 and IL or IK2 and IL all will remain same. That means, AK1 is equal to your IK1 upon IL or AK2 is equal to your IK2 upon IL, they will become real quantity, right. So, that means, this angle we will assume they are same for all the your what you call that all the load currents, right. That means, AK1 and AK2 both are real numbers, right, real quantity. So, that means, that is why I have written here above two assumptions suggest that IK1 and IL have the same phase angle, and so IK2 and IL, this leads us to the conclusion that current distribution factors AK1 and AK2 are real quantities. Thank you, again we will come back.